everybody, welcome to our last lecture about linear algebra with me. We're going to talk about diagonalization of symmetric matrices. Big idea is we want to find some equivalence statements for A when A is a symmetric matrix, kind of like we did for the invertible matrix theorem. A was invertible and we got a long laundry list. We're not going to have a laundry list quite that long, but we're going to get some cool stuff. So let's jump in. First off, what does it even mean for a matrix to be symmetric? So a matrix is going to be symmetric if you can write it being equal to its transpose. Notice that this is going to force it to be square. If A is m by n, the transpose will then be n by m. Can't be equal if n and m are not the same. So M is going to be, or A is going to be square for any symmetric matrix. For example, just to highlight, this guy kind of looks symmetric-ish in my opinion. And while it's pretty cool, it is definitely not going to be equal. So, not symmetric. B, on the other hand, if you take this transpose, the 3 swap corners, these 2 switch places, but 2 switching place with 2, that's not interesting. Or it is interesting, that's why we're talking about it, but it doesn't change. So B is going to be equal to its transpose. C transpose, this is another interesting, we'll say, matrix. But when we take his transpose, he ends up looking like this. And so you've got these 5s are across from each other. These 2s are across. In fact, everything going through is, it's got symmetry through the origin sort of thing going on. But what we need is if you make the diagonal you put a mirror across that, you need to have a mirror reflection, and that's not what's going on. So you can see if we do that for B, here we go, mirror reflection, that is what's going on. Okay, so symmetric, think mirror reflection across the main diagonal. First thing we're going to do, we're going to jump straight in with interesting results for symmetric matrices. Okay, so if A is symmetric, then what we can get from this is all eigenvalues of A are going to be real, which is pretty nice, guys. Not having to deal with complex eigenvalues, that's pretty nice. I'm sure you guys have done it at this point and didn't love it. Okay. How do we prove this? Well, we are going to assume what we were told. A is symmetric. So then A equals A transpose. That is what we assumed. Now we want to prove that all the eigenvalues are real, which means we need to get an eigenvalue. We're just going to say let A have an eigenvector V with eigenvalue lambda. So then that means we've got this equation. And then remember when I told you that complex eigenvectors and eigenvalues come in pairs? So same idea, you just take the complex conjugate of both sides and you would get this. And so now the goal is to prove that lambda is real. Want to show lambda is real. How can we show it's real? if lambda equals its own complex conjugate. Like, the only way for lambda to equal its complex conjugate is if there is no imaginary part. Okay, so that's where we're going to try and go with this. So what I want you guys to think about is this, like, what would that be? So that's a fancy way of writing a scalar, right? That would be a 1 by n and n by n and n by 1. Okay. So what, only if I do a transpose. Okay. I'm going to work on simplifying this. So we've got a v, and I can group up a and v. I know things about that because eigenvalues. So we're going to bring in an eigenvalue like that. Bring the eigenvalue out to the front. And then we're going to say that this is the same thing as dot product. Okay. So we got somewhere. Can't really say much about that right now. But there's another way to go around simplifying this. Suppose I had grouped up A with that V transpose. So it looked like this instead. Oh, there we go. I'm going to pull the transpose out, which makes it look like this. And now I'm back to, I have an A transpose. I'm going to bring in the fact that it's symmetric. Because if I do that, now I'm back at like the eigenvalue problem thing right there. So that would be the complex conjugate of lambda, like this. But then transpose of a scalar, that's not really a thing. So we just apply that to the vector. And then dot product. Okay. So now we took the complex conjugate transpose times A times V, and we got two different results, which means those two results have to be equal to each other. So lambda V conjugate dot V has to be equal to this. All right. This is just a number. It is the same number on both sides. If I can divide by that number, I have lambda equals lambda bar, just like we wanted. So it's kind of gets too much into like complex numbers. Just believe me. So V is not a zero vector. Remember, V dot V is greater than 0 as long as V is a real vector. If we take it to the complex, we get a similar result, where if you do the dot product of V with its complex conjugate, you get that it's guaranteed to be bigger than 0, and I don't really want to, it's not a complex class. Okay, so here we are, we got lambda is equal to its complex conjugate, so then lambda is real, just like we wanted. This is what I would say is not a good exam question. This relied on what I would say is cleverness instead of applying things you know and like chasing down, I know this implies directly, like following through from definitions and invoking like one theorem. This involved a little bit too much creativity, so don't worry about this proof. Okay. Next, we get another cool result, but now about the eigenvectors. If A is a symmetric matrix and it has eigenvectors, any two eigenvectors with distinct eigenvalues, so like lambda 1 has an eigenvector and lambda 2 has an eigenvector, we're going to get that those vectors are orthogonal. Beep, 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 beep. Like that. So I'm not talking about if lambda equals 1 and has multiplicity 2 and he gets two linearly independent eigenvectors. Those are not the kinds of eigenvectors I'm talking about. Distinct eigenvalues, as in two very separate, different values. I think this is a more easy way to digest this theorem. The book had it phrased in terms of eigenspace, and I don't know. It was harder for my brain to read it, and so I'm going to guess that makes it also harder for your brains to read it. Okay, let's jump into this proof. Okay, so we have A is symmetric. And we want to show that any two eigenvectors are going to be orthogonal. So we need to come up with some eigenvectors. So let A v1 equal lambda 1 v1 and A v2 equal lambda 2 v2. And lambda 1 is not going to equal lambda 2 because we need them to be distinct. We want to show that v1 dot v2 is going to be 0. That way we can have that they're orthogonal. How do we do that? Well, let's just start with the dot product. Okay, there's our dot product. We can't really say much about him. I only really know things about my eigenvectors when I've multiplied by an eigenvalue. So let's do that. Let's start with lambda 1 times v1 dotted with v2. Now, that's a thing I can deal with. I know things about that because eigenvector stuff is being applied. v2. There we go. Only trick in the bag really right now is to use the transpose definition of dot product, which would be cool because that would flip our position of A and B. V1. Oh, I'm getting ahead of myself. Let's write it out, and then now let's distribute the transpose. Like, oh, now we have some A transpose stuff going on. That looks a whole lot like A is symmetric. Gonna use that. Fun fact. And I'm going to choose to group it up. So before it wasn't grouped up, doesn't matter what order you group things in, or it doesn't matter what order you do things in, as long as you keep this order. So that order has been preserved, and I choose to put my parentheses there because that will be helpful. Why is that helpful? Because now I can do something involving lambda 2. There we go. And then I can manipulate this so that lambda has been pulled out to the front. There we go. And then let's take that back to dot product. Okay. So, long story short, we have this now equals this. Kind of like last time, we end up with that's a number and that's a number. They are the same number. And so if we divide by those numbers, we will end up getting lambda 1 equals number lambda 2, which is bad. We can't have that happen. We said they weren't equal. So then how is it possible that we have this overall thing equals that overall thing? It's only possible if we couldn't divide by that number, aka that number is 0. So v1 dot v2 has got to be equal to 0 so that lambda 1 continues to not equal lambda 2. Therefore, we now have they are orthogonal. All right, that's pretty cool. And then let's just take this for a test run. Let's do an example. Let's find some eigenvalues. Let's find some eigenvectors. We're going to do it just for a 2x2. It's symmetric. Let's go ahead and check this out. Let's just to prove to ourselves this is actually going to hold. So we're going to first go get eigenvalues. So that's going to look like this. Nope, not plus. It's got to be a minus 16. I'm going to simplify to this, which is the same thing as lambda minus 1 lambda minus 11 is equal to 0. There we go. Okay, so we have our eigenvalues. Now we can use them to find our eigenvectors. So if we plug in 1, we end up with this augmented matrix. So that'll fall out pretty quickly. Okay, so then our solution is going to be V, which is equal to V1, V2, where V2 is going to be free. And then we can say that V1 from up here is going to equal negative 2 V2. There we go. So then this is going to be lambda 1. So my eigenvector for lambda 1 is going to be, I'm just going to go with negative 2, positive 1. Remember, I can pick V2 to be anything that I want as long as it's not 0. Okay, let's go to our next eigenvector. So these are the steps to get to the eigenvector. Remember, you can choose whatever you want for V2, and I don't like fractions. So I'm going to say that my second eigenvector is being multiplied by 2 so that I get 1, 2. No fractions, yay. And then last step, let's double check that these are indeed orthogonal. So that was, V1 was negative 2, 1. So the dot product looks like that. We do indeed have orthogonality. Yay! It worked the way it was supposed to. All right. So we just talked about like eigenvalues and eigenvectors, which means we've pretty much already started talking about diagonalization. So let's officially start talking about diagonalization. So example 3, let's go ahead and just start diagonalizing A, because we already got the eigenvalues and distinct eigenvalues and distinct eigenvectors, or linearly independent eigenvectors. I'm sorry, I'm talking too fast. So we know P comes from the eigenvectors. And then D comes from the eigenvalues. So then A can be written as -2, 1, 1, 2, 1, 0, 0, 11. And then -2, 1, 2, inverse, whatever that might be. Okay. Fun fact, we checked that the eigenvectors were orthogonal. So now these guys, so where the columns of P are orthogonal. Fun fact. In fact, that's so fun. We're going to keep talking about it. Remember, it doesn't matter how you scale your eigenvectors. I chose to not have fractions and to try and keep things as simple as possible. That is not the only choice. Why am I bringing this up? Because I want you to recall for me real fast that if you have orthonormal columns, you get P inverse equals P transpose. That's pretty nice. That is an even nicer way to calculate the inverse than the theorem 2.6 maybe for 2x2 matrices, especially since it only works for 2x2 matrices. If I was trying to do this for a 3x3, this would definitely come in handy. So I already have orthogonality. Can I get orthonormal? By the way, this was proven on exam 2, question 5, if you don't know where I proved that. So go check solutions. All right. So let's see if we can get orthonormal. So eigenvector 1, that was -2 and 1. The magnitude would be equal to, square root of 5, which means our unit vector would be -2 root 5, 1 root 5. Then just again to reiterate why this is so okay, U1 is in the span of -2, 1. And as long as you're picking a vector from your eigenspace, this is our eigenspace of A associated with lambda equals 1. So anything from that eigenspace is an eigenvector of lambda equals 1. It is a linear combination. The linear combination is 1 over root 5. Let's do it again. V2. Same magnitude, same story. So now we have orthonormal columns for P. That's pretty cool. Let's see, do I have space? I do not have space. Okay. Let's shrink this real fast so that I can talk about this. Okay, so let's write A using these eigenvectors instead. So A equals, -2 root 5, 1 root 5, 1 root 5, 2 root 5. D stays the same because that's just eigenvalues. Then -2 root 5, 1 root 5, 1 root 5, 2 root 5. Where we want to take the inverse of this matrix, but now, handy, P inverse is going to be equal to P transpose. So all we have to do is take a transpose. That's much easier. So now A is going to equal see transpose of this, these guys switch spots. I'm sorry, you keep hearing timers go off. My child is making lunch. Okay. So there we go. Nice and easy. And in fact, when we're able to do this, it's actually so cool. We're going to have a name for it. Here we go. We say that a matrix is orthogonally diagonalizable if you have a diagonal matrix, D, and P with orthonormal columns, such that you get to replace P inverse with P transpose. So that's what we just did. We just orthogonally diagonalized A. That's I'm going to ask you to orthogonally diagonalize a matrix in your worksheet, and so you're going to do exactly what I did for A. All right. I want to chase something down. You may or may not have noticed, let's flip back for a moment. We're back at P. That is on purpose. That was not a coincidence. So check it out. So if A is orthogonally diagonalizable, we get this. So let's take the transpose of that. That means transpose of all of these guys, which means we have to flip it backwards, double transpose on that guy. Okay, but a double transpose is just the original matrix, and then transpose of a diagonal matrix is itself. But wait, that was A. So if it is orthogonally diagonalizable, that means A has to be symmetric. That's so cool, it deserves a theorem. So we've got if A is orthogonally diagonalizable, if and only if A is symmetric. So this is actually a two-way street. If we get symmetric, we also get orthogonally diagonalizable. Oh, I don't know why that is such a tongue twister for me. I cannot talk. Okay, so if and only if statements. You got to prove it going both directions. Going forward, start with orthogonally diagonalizable and get to A is symmetric. We just did that. And then the other direction would be start with symmetric and get orthogonally diagonalizable. I don't think that this proof is particularly insightful. I thought it was too hard with too little gained. And so we're going to say beyond the scope of this lecture. And we're going to call it good. There we go. Good enough. Okay. So cool theorem. Going to give us something else. We can continue to chase this down. So what we have is symmetric implies diagonalizable. So if it's diagonalizable, though, this has an implication about the eigenvectors. So we always have enough eigenvectors, or enough specifically linearly independent eigenvectors, to construct that matrix P. Remember, we had a problem before where we had an eigenvalue and it had a multiplicity problem. It had more than one. It was like lambda equals 1 and lambda equals 1 again. And so it's like, okay, that's fine as long as we can find two linearly independent eigenvectors to go with lambda equals 1 showing up more than once. But sometimes we couldn't always get two linearly independent eigenvectors to go with our multiple values of 1. That has been solved. Symmetric means diagonalizable. So as long as we're symmetric, we're going to have enough linearly independent eigenvectors to construct that P matrix. Otherwise, it wouldn't be diagonalizable. So then the fallout from that in fancy speak is the multiplicity of lambda equals the dimension of the eigenspace of lambda. Remember, the eigenspace of lambda would just be the linearly independent eigenvectors associated with lambda. So number of linearly independent eigenvectors associated with lambda. Because, right, when you solve it out, like lambda equals 1 and lambda equals 1, hopefully you're going to get v equals, and then that plus maybe like v5 or something. And then these two vectors would be linearly independent, and they form basis for the eigenspace. Okay, hopefully that's enough of a reminder if that definition has fallen out of memory. Okay. So all we've done so far is we've gone symmetric and gotten something cool. Did symmetric, we got something else cool. And we just keep on getting cool things for A is symmetric. We summarize all these things into the spectral theorem for symmetric matrices. It's not as big as IMT, but we still get some really cool results. So we already proved that. And then I just proved that on the last slide. And then we already proved that. And we already proved that. So there we go. If A is symmetric, we get some pretty cool things about diagonalizing it, which gives us really cool things about its eigenvalues and eigenvectors. Just a note for why it's called the spectral theorem. Sounds so important. It comes from the word spectrum. The collection of eigenvalues for a matrix is called the spectrum of a matrix. And here we are talking about its eigenvalues, and we want to include all of the multiplicities, which gives us those really cool things about eigenvectors always being linearly independent, which is why we end up with spectral theorem, is because we got some really cool things by looking at the entire spectrum of a symmetric matrix A. Okay. I think that's all the time we have for right now. This does give us even more cool things that I wish that we had time to talk about, but this is going to be our last lecture, and so I hope that it wasn't boring. Hope we ended on a high note. Anyway, I'll talk to you guys all in a little bit, but never again in lecture.